Hello, my name is Keith Hodge, and I'm here to talk with you a little bit today about compost process modeling in SWOLF. A quick look at what we're going to cover today in this presentation. We're going to introduce composting as a treatment option for organic wastes. We're going to look at some of the mass flows involved in a composting setup, explore some of the technologies available when it comes to exactly how composting is achieved, and then look at some end product uses for the final compost product. And finally, we'll look at some illustrative results from the process model. So composting is a biological process in which organic matter is decomposed aerobically, meaning airflow, in particular oxygen flow, is critical to the composting process. And as we'll see once we get into some of the specific technologies, how that airflow is achieved is a critical distinguishing point between the technologies. So with the addition of oxygen to organic matter in the presence of microbes, we have the release of CO2 and water vapor and heat. There's also some other minor constituents that are released, and we'll get into that a little bit more. So in the context of the larger solid waste system, composting is here, and it touches several areas of the larger system. It's a receiving point or potential receiving point for organics, whether from separate organics collection or from potentially a mixed waste MRF, and residual from composting needs to be treated as well through thermal means or disposed of in a landfill. In our standard conceptual overview of a process model, we see there's waste materials coming in, those are predefined, and then we have specific user inputs that give us the definition of our composting process. And coming out at the bottom we see contaminants and the final composting product, and then there's all these fuel use, emissions, costs, etc. that are integrated with the other models. So, organic matter. This is what we're putting into the composting process. So, organic components in MSW is what we have included in the SWOLF package right now. That includes primarily yard waste, which may include some paper products as well, and then food waste and potentially some separate papers. There are certainly other materials that can be composted, including potentially sewage sludge and ag wastes and some other items, but those are not directly included in SWOLF right now, but can always be added if data is available. So what are the objectives of composting? Why do we do this? We want to reduce the volume of waste that we're handling, and you get a useful product out of it. Also, it is one of the better ways to divert material from the landfill, divert organic material from a landfill, and we can avoid some of the methane emissions that go on in a landfill, because that's an anaerobic environment. We get methane production. The goal of composting as an aerobic process is to produce carbon dioxide instead, which is a less potent greenhouse gas. So as I touched on in the previous slide, we see here on the left is 1 megagram, 1,000 kilograms of waste product starting or entering a composting process, and after 21 days of composting, but fairly standard residence time. We can see that a lot of the mass of water has been lost, and the fast degrading volatile solids are all gone as well, and a portion of the slow degrading volatile solids. So what we end up with here is, you can see from the left we have 1,000 kilograms, on the right we're down to about 400. So pretty significant mass reduction. So here is a little bit more detailed view of what might happen. This is running with some default values. I'll step through these processes. So at the very top we have 1,000 kilograms of waste coming in. It goes through primary, secondary screening just to get rid of some residual contaminants, and then we end up with a mixing stage where we add those incoming waste products to potential amendments, none in this case, but may need to add some water as well. Then from mixing we go to the active composting, which I believe these results are for a windrow. We can see headed off to the right there from active composting is off gases. That's a pretty significant loss of mass there. From that we head down to post screening. There's a certain amount that's recycled back into the mixing, to the front end of the composting, and there's a certain residual as well. A vacuum pulls off some other light residuals, and ultimately goes to a curing stage where there's further off-gassing, and finally at the bottom we have a finished compost, and in this scenario we ended up with about 330 kilograms out of the initial 1,000. Here's just a quick overview of some of the critical mass flow inputs for the life cycle model. These have largely to do with biodegradation and the off-gassing that occurs in the active composting phase and in the curing phases of the process. Mostly it's looking at carbon and nitrogen loss and exactly what those losses end up as. So carbon, some of it goes to methane, nitrogen, some of it goes to nitrous oxide, both of which are critical greenhouse gases. So a couple general inputs to the model. These are inputs that apply to all situations, meaning each technology has some differences, but these inputs apply to each technology. So we have some fuel use parameters, some electricity use parameters, and just some timing. Now just talk a little bit about the technologies. There are 4 big technologies out there, and we have capability to model each of them in SWOLF. I'll start to cover them in detail now, starting with windrows. So windrows are a long pile essentially, and of a certain size that depends on your equipment usually. And typically you are turning these things as much as daily to maybe a few times a week, and generally the way that you're getting oxygen to your waste material in this case is by turning it. So there's a machine that comes down and just fluffs up the material, essentially gets what's on the inside to the outside, and make sure we over the course of several days get oxygen to all of that material. Here's a quick picture of that windrow turner and a quick overview photo. You can see the long piles. This is a pretty big site that has many windrows. So key inputs here, the composting time, that's how long the active composting phase lasts. Has to do with the space it takes up, for example. A typical turning frequency here we have 3 days, every 3 days, and there's fuel use associated with that windrow turner. The next technology option is referred to as the aerated static pile. The static pile in this case just meaning that it's a pile of material that's really not turned in the same way that windrows are, and aerated meaning that there's pipes with a blower underneath the pile that provide airflow through the pile. Sometimes these are located inside, sometimes outside, and a lot of times it is common for a finished compost product to be placed over the pile, providing a layer of insulation, and it helps with odor control as well. So here's just a quick schematic. There's a couple different ways to do this. You can suck air in through the pile or push air out through the pile. Either way, you're getting air contact through your compost. And in both cases, odor control is important. You can see it's maybe a little easier to control on the suction aerated option. You can just put a filter on your output. So key input here, or key inputs here, you can see that the active composting time is quite a bit shorter than windrows, and we have an electricity use value here for essentially just the blowers. GORE covers are a modification on the aerated static pile concept, but they incorporate this membrane cover system made by GORE, so it's a proprietary system, and so we still have the aeration component below this pile, but they're often shaped in a windrow type configuration, and the membrane serves a few functions. It keeps water, specifically rainwater, off the pile, and it also has sort of a selective permeability in terms of the gases that can leave the compost pile. So it lets carbon dioxide leave, but it holds back some of the other more complex compounds that are associated with odors and other issues. So a few key inputs for the GORE system. The active composting time is typically about 30 days, and that's again less than the windrow system, maybe a little bit more than the aerated static pile. We see here that electricity use is a little more than the aerated static pile, and again that's associated with aeration. Finally, we come to in-vessel composting. This is the most expensive option, but in some ways it's also the Cadillac option because it gives you the most control over the composting process in terms of aeration, temperature, exactly how the process goes. You have a lot more control over some of those variables. So this can be either in a rotating drum configuration like the photo here, or it's set up similar to an indoor aerated static pile. A few key parameters here. Again, we have a relatively short composting time, and here you can see that the electricity use is much higher than all the other options. So the end product, what we think of as compost. What can we use it for? Well, it's useful as a soil conditioner, potentially. The organic content improves soil, and one of the specific things it does is improve the moisture holding capacity of the soil. But it also contains nutrients, and that of course depends on the feedstock that you're using. Nutrients aren't just pulled out of the air. There's got to be some nutrient content in the waste that you're bringing in, and it's critical with compost to have a good idea of your markets before getting into this business. But there are a number of options out there. One of the maybe least preferable options, or the maybe the least bang for your buck, would be using it as landfill daily cover, and that might be an option if what you're composting is a mixed waste material. It's not source separated organic waste. That might be a good option. But here's a little bit higher quality options, selling to nurseries and landscapers, for example, or potentially even in agriculture as a nutrient source. So in our model, you can handle this a few ways. No offset for the end use, or potentially a fertilizer offset, or a peat offset for use as a special soil amendment. In this table we have some of the model input parameters that we use to describe emissions associated with the final compost usage. And the first two have to do with land application of the compost material, how far it is, and the diesel use involved. And then we come to two that relate to carbon storage. The first one here is a default of 10% of the carbon that is stabilized carbon from the original organic matter now in the final compost material. We say that 10% of that is remaining in the soil, remaining bound to the soil after 100 years. So we count that as a carbon storage benefit. Then the next line item there is related to the additional carbon sequestration that is associated with our initially putting the compost into the soil. So finally, the last two have to do with some of the nitrogen balance, and part of it is nitrogen in the compost that is released as nitrous oxide, which, as we discussed before, is a critical greenhouse gas. And finally, the last item in this table is a ratio that relates the amount of nitrogen in the compost to the amount of nitrogen mineral fertilizer that we're offsetting. Then if we're talking about potential fertilizer offsets or peat offsets here, this is just a quick overview of what you're offsetting. So for every kilogram of nitrogen fertilizer equivalent, you're offsetting about 5 kilograms of CO2 emissions, for example. Okay, some quick results. This is from a study we did where the functional unit was 1 ton of food waste plus about 600 pounds of yard waste. And you can see the breakdown here. We're looking at global warming potential. We see our horizontal zero axis. Everything above that is an emission. Everything below that is an offset. Things that jump out right here: the biodegradation is the orange on top, and I mentioned that one of the key inputs is the proportion of the carbon that goes to methane and the proportion of the nitrogen that goes to N2O. Both of those have a big impact here on the global warming potential. And then the carbon storage is what I was just speaking about. Has to do with the organic carbon from the waste products being bound in the compost and presumably left in the ground then, and we get a big credit for that. So as you can see, there's some variation across the technologies. Electricity use pops up, particularly with the in-vessel and the aerated static pile systems as an emission. Okay, and this, we're looking at a different metric. We're looking at total energy use, meaning total fossil energy use. And what we're looking at is, once again, the zero axis. Emissions are on top, and electricity use is a really big one for the aerated static pile and the in-vessel system. And the primary offset that we have in this case is the fertilizer offset, so the fossil energy that goes into producing NPK, mineral fertilizers. So again, we're doing the same thing here, except instead of looking at global warming potential, we're looking at total energy use, which refers to fossil energy usage. And in each case here, you can see that the offset, or that portion below zero, is fertilizer. There's a certain amount of fossil energy that we're saying we no longer need to put into fertilizer production. So that counts as an offset, and there's pretty significant electricity use for these heavily aerated options. So you can see quite a difference between the technologies here. So that's all I have for now. References, you can see here some of the sources we used in the process model.